Today we will delve into a crucial topic affecting blast furnace operation worldwide: the impact of moisture generation during the water quenching process on overall coke quality and performance. Our central finding is clear. There is a direct correlation where high moisture leads to poor coke strength after reaction and high Coke Reactivity Index. The best quality coke is consistently linked to low control moisture values. Now, coming to our this slide where we start with the basics of water quenching. This is a crucial step in coke oven operation involving rapid cooling of red hot coke which exceed the oven at temperature exceeding 1000 degrees centigrade. The primary purpose of this water spray process is twofold: to prevent coke from air burning and to prepare it for subsequent handling and transport. The actual cooling takes place within the quench battery, a structure equipped with a spray nozzle and a collecting pit. Unfortunately, while cooling, the coke, due to its porous structure, readily soak up water. Furthermore, the rapid cooling process acts to trap water inside the coke lump and within micro cracks. So after the quench process, moisture level in the final coke typically range between 5 to 12%, though they can be higher if the process is not tightly controlled. This high moisture level is detrimental. As mentioned earlier, coke strength after reaction, that is CSR, consistently falls as moisture increases while coke reactivity index simultaneously rises. High moisture has immediate negative effect on physical properties. First, cold strength is reduced. This reduction is attributed to crack formation and general surface weakening. Second, the coke's abrasion resistance is lowered. This means the coke is more susceptible to breakage, generating excess fines during handling operations. Beyond the strength, high moisture affect thermal and chemical properties. Damp coke conduct heat less efficiently, reducing its thermal conductivity. Critically, moisture causes surface changes that can increase the coke reactivity index, that is CRI, meaning it reacts more radially with CO2. Ultimately, this leads to poor size stability with more fines generation with the brittle lumps. The negative effect of damp coke are magnified in blast furnace. The primary energy impact is that more heat is consumed simply for water evaporation, which is a significant waste of energy. Additionally, this evaporation generates steam within the furnace, fundamentally altering the gas chemistry necessary for efficient operation. So perhaps the most severe physical consequences is generation of fines. These extra fines worsen permeability inside the furnace, which chokes the bed and drastically increase the pressure drop. Operationally, this leads to much more unstable condition, increasing the risk of burden slip or hanging. Due to this inefficiency, a higher coke rate is necessary just to maintain the same level of hot metal production. The data confirms that performance is tied directly to moisture. That is, coke with moisture below 5% exhibit high mechanical strength, good permeability, the best energy efficiency, and low fines generation. Conversely, Coke above 10% moisture shows poor strength, bad permeability, and worst energy efficiency. Uh, so we can say uh, a lot of things based on the statistics and on recent study published in 24 and 25 further confirm these findings. Higher moisture, whether from quenching or cold feed, increases the coke porosity, reduces the strength, and accelerate reactivity. Specifically, water, including industrial coking wastewater, interacting with hot coke during quenching, increase surface damage, alter the pore structure, and intensify the gasification reactivity. The presence of water is damaging, but the impurities are also a fact. Water derived organic compounds can further weaken the coca structure, modifying functional groups and as characteristics. Ultimately, moisture and any accompanying water impurities accelerate coke breakdown, compromising bed stability, permeability, and abrasion resistance, directly affecting the blast furnace. It is not only the quench process that matters. Study shows that high moisture content in the cool feedstock itself result in less dense coke, increased porosity, and high variability in the size and strength. Furthermore, internal steam pressure generated from these moisture cases uh, are the main cause of rapid expansion and micro cracking within the coke oven, which reduces the mean pore size but increases overall porosity, increasing to the very higher reactivity and lower strength. Fortunately, solution exists. Tata Steel, for instance, implemented Coke Dry Quenching, are replacing traditional water quenching. Before CDQ moisture average 6 to 10%. After implementing, it's coming around reduced to below 2%. The results were impressive. CSR improved by 10 to 15 points. CRI stabilized at lower value and fines at the blast furnace top reduced by 20 to 30%, which is a very impactful value. Beyond CDQ, the moisture control is key. At JFE Steel, adjusting pre-drying and blending to keep coal moisture in a narrow band of 7 to 8% led to coke with a higher mean size and improved handling properties. Empirical regulatory case study confirm the financial and operational benefit. Every 1% reduction in coke moisture result in 2 to 3% increase in CSR and 2 to 3% reduction in fines. So real-time monitoring systems have also confirmed that lower moisture leads up to 20% improved mechanical strength and blast furnace permeability, and which has a huge impact in the blast furnace. To conclude, the message is simple but vital. High moisture in coke equals poor coke performance in the blast furnace. It reduces the strength, boosts fines, wastes energy, and severely hurt gas, and liquid flow. To sustain top cook quality and furnace performance, expert team must prioritize the monitoring, control, and optimization of moisture levels.